Bismillahirrahmanirrahim. Today we are going to talk about chapter 4, Inequalities. Previously we have talked about number systems, real numbers, and states and proofs. Okay. Now we know that we have bunch of inequalities, almost which is greater than or equal to. We have less than and less than or equal to, and what is an inequality? So an inequality is a statement about real numbers involving one of these symbols these symbols and for example we can have x is greater than 2 or x square minus 4, y is less than or equal to 2x plus 2. So these type of statements involve the inequalities. And there are some certain rules they follow, the inequalities follow, and we will show and prove. We will use those rules to solve these types of equations which involve the inequalities. Okay, these type of inequalities though, these are not called equations, my bad. Okay, so let's write rules. Let's say 4.1. This is if we take x a real number, then either x is greater than 0 or x is less than 0 or x is 0, and just one of these is true. So this is rule 1. 2, if x is greater than y, then minus x is less than minus y. Rule 3, if x is greater than y and c is a real number, then x plus c is also greater than y plus c. Number 4, if x is greater than y and y is greater than 0, then the product is also greater than 0. 5, if x is greater than y and y is greater than z, then x is also greater than z. These are the rules we follow to solve inequalities. Let's do some examples. If x is less than 0, then minus x is greater than 0. Let's prove it. Applying rule 2, which says that if x is greater than y, then minus x is less than minus y. 2, with 0 instead of x, with 0 instead of x and x instead of y, we see that x is less than 0, then minus x is greater than 0. Okay. Example. If x is not 0, then x square is greater than 0. And to show that, consider that if x is greater than 0, then by 4, x square is x into x greater than 0. If x is less than 0, then minus x is greater than 0. By above example. So 4 is what? If x is greater than 0, y is greater than 0, then the product is greater than 0. 4 gives minus x into minus x greater than 0, i.e. that will be x square greater than 0. Perfect. Next one says that if x is greater than 0 and u is greater than v, then xu is greater than xv. This is a bit tricky one, but we can prove it. So this says we have u is greater than v, then u minus v is greater than 0, which is greater than v minus v, which is 0. V minus v, which is greater than 0, and this can be done by 3 with C is minus V. Then X into U minus V is greater than 0 by 4. Then XU minus XV is greater than 0. Then XU minus XV plus XV is greater than XV. And this is again by 3 with C is XV. Then this shows XU is greater than XV. Perfect. Similarly, we can say something more. Example, if U is greater than V, which is greater than 0, then U square is greater than V square. Let's prove it. So by for the simplicity, let's name these. This is 4.1, 4.2, 4.3. By example 4.3, give U is greater than V, then U square is greater than UV, and U is greater than V, then UV is greater than V square. Hence, U square is greater than V square by 5. Another thing is, let's say if X is greater than 0, then 1 over X is also greater than 0. Let's prove it. Assume if X is 1 over X is less than 0, then minus 1 over X is greater than 0 by example 4.1. So by number 4, rule number 4, X into minus 1 over X is greater than 0, i.e. minus 1 is greater than 0, which is a contradiction. Therefore, 1 over X is greater than or equal to 0. Since 1 over X can't be equal to 0, we conclude by 1 by 1 that 1 over x is greater than 0 only. And that's how we prove it. Example. So these are just statements we are proving by using the name example. Okay. So that's how we do that in this lecture. Okay. Another one. So we have another one, which is 4.4. This is 4.5. This is 4.6. Late x1, x2 to xn are real. And suppose that k of these numbers are negative and the rest are positive. If k is even, then the product x1 product x2 up to xn is always greater than is greater than 0. And if k is odd, then the product is less than 0. This is interesting. So you have bunch of real numbers and you say that k of them are negative and the rest are positive. Now, if k is even, then the product of these real numbers is positive or greater than 0. And if k is odd, then the product of these numbers is negative or less than 0. And to prove this, we say since the order of the xi's does not matter, we may as well assume that these numbers are negative, x1 up to xk, and the numbers from x1 xk plus 1 to xn are positive. Okay. Then by example 4.1, minus x1 to minus xk, comma xk plus 1 to xn are all positive. Are all positive. by rule 4, the product of all of these is positive. So -1 power k, x1, x2 up to xn is greater than 0. Now, if k is even, this says that the product is greater than 0. And if k is odd, it says that -1 minus x1, x2 dash dash x n is greater than 0, hence it is less than 0. True. Okay. Now we will solve some typical inequalities. These are the properties. Now we will solve some inequalities. So be like this. Okay. Example 4.7. For which values of x is x less than 2 over x plus 1. Solution. First, a word of warning that we cannot multiply both sides by x plus 1 is this may or may not be positive. So we'll proceed more cautiously, subtracting 2 over x plus 1 from both sides gives the inequality. So what we will do x minus 2 over x plus 1, this sign 2 over x plus 1 minus 2 over x plus 1, and then we will have x minus 2 over x plus 1 less than 0. Now, what we can do is we can write this as x plus 2 into x minus 1 over x plus 1, which is less than 0. Now, by example 4.6, this is true if and only if either one or three of the quantities is negative. This is true if and only if either one or three of the quantities, which quantities that x plus 2, x minus 1, and x plus 1 are positive. Oh, sorry. Is negative because they are less than 0. All three are negative when x is less than -2. All 3 are negative when x is less than -2, and just 1 is negative when -1 is less than x is less than 1. So this is the answer. So these are the values that x is less than 2 over this. Okay. Example 4.8. We need to show that the quadratic inequality is greater than 0 for all x in the reals. Solution. Note that x square plus x plus 1 can also be written as x plus 1 over 2 square plus 3 over 4. You can write it by using the completing square formula or something like that. Hence, by example 4.2 and rule number 3, we have x square plus x plus 1 is greater than or equal to 3 over 4 for all x. For all x. Okay. Perfect. Now, we can define something, modulus of a real number. Modulus of, maybe there's O. Sorry, there is U. Real number x in R. So we write it with this symbol, and it is x and minus x both varies on the values x is greater than or equal to 0 if x is less than 0 only. For example, mod of -5 is 5 and mod of 7 is 7. Example 4.9. Modulus square is x square and mod of xy is mod of x, mod of y for all x comma y in R. Let's prove this. So we say if x is greater than or equal to 0, then mod of x is x only. And mod of x square is x square. And if x is less than 0, then we say mod of x is minus x. and mod of x square is minus x square, which is x square again. Right. So it is cool. Second part is an exercise. You can use this same way to show that. One thing which I'm curious about is that we know that mod of x measures the distance from the point x on the real line to the origin 0. Thus, for example, the set of values of x such that mod of x is less than or equal to a for some point a on the real line consist of all x between minus a and a, which we can write is minus a less than or equal to x, x is less than or equal to a. And that we can formally say as follows. By an example 4.9, thanks for 10. Okay. We say that we have two real numbers a comma b in R with the condition that b is greater than 0. Now, for which values of x is the inequality less than or equal to? So, let's say for which values of x is the inequality, which inequality x minus a is less than or equal to b satisfied. So to show that, let's find out the solution or talk about it. So when x is greater than or equal to a, we get x minus a is less than or equal to b. That is, x is less than or equal to a plus b. And when x is less than a, we get a minus x is less than b or equal to b. That is, x is greater than or equal to a minus b. So the range of values of x satisfying the inequality inequality is what? A minus B is less than or equal to X. X is less than or equal to A plus B. Perfect. In the similar fashion, we can talk about the triangle inequality. The triangle inequality, which is x plus y, mod of x plus y is less than or equal to mod of x plus mod of y for any x comma y in real. Okay. And to prove this, by example 4.9, we have what? We have, if we square this, what we will get? We will get x plus y square. Then we will get x square plus 2xy plus y square. Then we will get, we can write this as mod of x square plus 2 into x into mod of y plus mod of y square, which means that we can write mod of x plus mod of y whole square. And if this is equal to this one, then you can surely see that we can say that mod of x plus y is less than or equal to mod of x plus mod of y. And this is by example 4.4. We will end our first over chapter number 3, which number 4, sorry, here with all these examples. See you in the next lecture.